Daliang from Johns Hopkins here telling us about the connection between conformal blocks and quantum gravity.
Thank you. Thank you for inviting me. It's great to be back. Today I will be talking about some of my recent work, trying to understand aspects of quantum gravity using ADS-CFT correspondence. This is mostly based on this paper, but I will also touch on results from these two papers as well as some ongoing work. All of these are done in collaboration with different combinations of these great collaborators. So the conjecture of ADS-CFT duality is saying that if you put the mysterious soup of quantum gravity into a can, and then whatever is written on the label of the can, the battery just died. Whatever is written on the label of the can should give you a full, complete, and exact description of what is inside. So we, is it working? That's okay. So we take advantage of this. We assume that this duality really holds. So it will allow us to try to understand what is quantum gravity from what we know about the conformal field theory that lives on the boundary. In this talk, I will be focusing on the case of three-dimensional ADS and two-dimensional CFT. Thank you. The reason is that this is probably one of the simplest incarnations of this duality. In particular, gravity in 3D is simple because it's topological. It doesn't have local excitations. And the two-dimensional CFT is simple because it has an enhanced infinite dimensional symmetry known as the Virasoro symmetry. So both of these facts will work in advantage for us and enable us to get some exact results on this subject. So some simple facts about ADS-CFT. So the graviton in the box is due to the stress energy tensor on the boundary. And the Newton's constant is inversely related to the central charge in the CFT, which roughly describes how many fields do you have in that field theory. So armed with this very powerful tool, what is the problem we want to address? So of course, there are many, many mysteries in quantum gravity. And one of the most controversial subject is the black hole information paradox. This paradox is saying if you have a black hole and you throw something into it, is the information associated with the infalling matter erased by the black hole, or is it preserved in some complicated, mysterious way? If you believe in ADS-CFT, of course, you should believe that the information is not lost, it's still there. But then you have to understand how to reconcile that with the fact that Hawking radiation looks so thermal. This is most famously recently discussed in the as the firewall paradox. But we will not get into the firewall paradox in this talk because the question of whether you have a firewall is not that easy to formulate in the context of CFT. So we cannot yet define the local observable in the bug inside the horizon from the CFT perspective unambiguously. So this is, in the CFT, this is the question of bulk reconstruction. So how can I reconstruct a local observable in the bulk using data from the CFT? There are many work and ideas on this direction, but I don't think there is an unambiguous procedure to do that, especially when the point is inside the black hole horizon. Instead, in this talk, we will focus on two much easier signatures of black hole information loss. One of them is what I call the late-time decay, and the other one is the forbidden singularity. I will explain these signatures in detail later on. So first, let's look at how to get black hole physics from the CFT. All of this will be explained in much more details later. This is more like a preview. So in the most standard dictionary of ADS CFT correspondence, a black hole in the bulk is usually thought of as due to a thermal background on the boundary, where the temperature on the boundary is the Hopkins temperature. But if you adopt this point of view, then you have to conclude that the black hole in the bulk is not in a pure state, it's in a mixed state, because the boundary is thermal and a thermal state is a mixed state. Of course, we know that we can create black holes in a pure state. For example, you can shoot a lot of such lasers and assume you can shoot them in such a way that they're coherent. And you shoot a lot of lasers into one point in the bulk, and you can collapse a black hole, and that's going to be in a pure state. So then comes the question of how does a pure state black hole mimic the behavior like a thermal background? Of course, more precisely, we can represent our pure black hole state as this. And then we can measure the expectation value of some observable within this state. And we expect that this will approximate the thermal expectation value of the same observable. We will show that this actually do happen when you take a particular large C limit for the CFT. But of course, when you have that, when you have the thermal behavior of the black hole, you also have the information loss problem. So this is basically saying that we can get the signature of information loss directly from the CFT. You will see in a lot of detail how this is done. But before we go into that, we can already see the first signature of information loss. That's the late time decay. So let's say now we create a black hole in the middle of ADS by acting, we just create a pure state black hole. And we perturb that black hole by putting in some perturbation at t equals 0. And we wait for time t, and then we measure again on the boundary. We make a measurement to see whether the perturbation is still there. Of course, classical black hole physics will tell you that this measurement will decay when you increase t. The longer you wait, the smaller the chance that you're going to measure that perturbation again. This is because whatever energy you perturb it with, it will fall into the black hole. So you wait for enough time, then all of the perturbation falls into the black hole, and you cannot measure what you put in the beginning. But this expectation is not, but from the perspective of a boundary quantum system, this is not the correct expectation, because we can insert a complete set of energy eigenstates here, and we can expand in that eigenstate. Then we can represent this Vt function as a sum over all these oscillators. Then for any quantum field theory defined on a compact space, such as a circle here, it will have a discrete set of energy levels. And this discreteness will tell you that this sum will decay initially because the different phases do not line up and they tend to cancel each other. But if you wait long enough, the decay should stop because you just have a discrete set of eigenvalues and they cannot completely cancel each other. And that discreteness can be measured by the black hole entropy, which basically tells you in a small interval of energy how many states are there. And you expect that this V should stop decaying when its magnitude is roughly in the order of e to the minus black hole entropy. So this behavior of this V variable stop decaying is already colliding with your classical expectation that V should just decay. Of course, if you wait long enough, there's even more peculiar behaviors because these phases can line up if you wait long enough, and they will create the V will basically decay initially, and you wait long enough, it's fluctuating at this very small value, and you wait like very, 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 very long, it will emerge again from this randomness and becomes order one again. So this is a version of Poincare reoccurrence. It only happens at very, very late time. but we will not be talking about this large time scale in this talk. But you can already see that whichever argument you choose, you cannot believe that this V should decay indefinitely. So this is our first signature of information loss, is that this correlation function should decay. But before we go there, we have to go through some basics of ADS3 FT2. Basically, as we said in the first slide, graviton in ADS3 is due to the stress tensor in FT2, and you can expand the stress tensor in terms of modes, and each mode operator is a Virasoro generator. And the first three Virasoro generators generate the global conformal symmetry. So these three guys will annihilate the vacuum. But you also have these other modes that will, when they act on the vacuum, you will not get zero, you will get a graviton state. So they will generate a graviton, and these guys will destroy a graviton. So one way to think about this is that a graviton is a Nabu-Goston boson of the spontaneously broken Virasoro symmetry. Of course, you can now start organizing the Hilbert space of 2D CFTs in terms of Virasoro multiplets. In particular, you can start from a highest weight state that is annihilated by all the destroying operators. And then you can act on them with the creation operators of the graviton, and you get infinite multiplet of such states. Then all of them are related by Virasoro symmetry. So they're basically describing some object together with that object plus some number of gravitons. This is what a Virasoro multiplet means. Once you have this, you can decompose a correlator in terms of contributions from different multiplets. That's what I've written here. So basically, the point is that this V function is defined as a Virasoro block. Its form should be fixed by the Virasoro symmetry completely, and these OP coefficients C, H bar are determined by dynamics. They're not fixed by the symmetry. Although we know that this V is fixed by symmetry, it's actually very difficult to get the explicit form of these Virasoro blocks. But today we will be working on some specific limits where we have more control over these functions. So this is writing out a Virasoro block in more detail. So this is explicitly writing that I'm inserting a projector in between this correlator. And this projector projects onto one particular Virasoro multiplet generated by this highest weight state. And in the bulk, you can think of this as the contribution from exchanging this particular state plus exchanging a indefinite number of gravitons. Of course, with this perspective, you already see that a Virasoro block already have a good amount of quantum gravity packed inside it because you're summing over all these graviton exchanges. And in particular, one very interesting block is the vacuum block, where this H is just 0. So the vacuum block is just a contribution from pure gravity. And it's actually universal. It should exist in all two-dimensional CFTs, all unitary two-dimensional CFTs. So this vacuum block will be our primary focus today, although a lot of the techniques will be generalizable to other blocks as well. So now we can see how to get the thermal black hole physics from CFT. We can create a black hole just by acting a very heavy operator on the vacuum. Where by heavy, I mean that this operator have a large dimension, which is due to the mass in the ADS. And then after we create this black hole, we probe it with some light operator. This light operator has small dimension or light mass, so it will not backreact significantly on the geometry. And this measurement is represented as this 4-point function. So we expect that if we go to a semi-classical limit described by a large C limit, but we still want a black hole, so we cannot just make the gravity go away. So we have to assume that when C goes to infinity, H heavy over C, H heavy is the H of this operator, the weight of this operator. This is kept fixed. And then H light is finite because it's just a prop. So in this limit, it's actually possible to just compute the Virasoro vacuum block. And this is the result. So this is what I call the semi-classical vacuum block. It is given by taking that limit over the exact Virasoro block. And you get this very, very simple function. And it actually have a very precise physical meaning. For example, here, this quantity TH just emerges when you take this limit. And this TH is given by this expression, which is exactly the CFT expression for the Hopkins temperature. And here, just a note that this Z is related to the Euclidean and Lorentzian time in this way. This is just the standard radial quantization mapping from a plane to a cylinder. What's amazing is that this semi-classical vacuum block actually matches the form of a two-point function for the light operators on a thermal background. So with
But you absolutely need that though, because you're claiming the other thing is a black hole. So the black hole should already, you're generating it from a vacuum with a heavy operator.
yeah, I think
So this had better work, right? Otherwise that's not right.
exactly. So this is more like a, I think it depends on your perspective, right? For me, I expect that to hold, but of course, some people will think, oh, you're just creating a black hole with a pure state. Maybe the pure state doesn't mimic the thermal background exactly, because this is thermal. This correlation function is calculated in a mixed state, in a thermal state, but this is calculated purely in pure state. So I think this is one way to think about this is that this is a precise formulation of the eigenstate thermalization hypothesis. So you can just create something that looks like a thermal background just by using a very high energy eigenstate.
Is your Blackhole operator OH is it a Virasoro primary or not?
It is, well, this is an interesting question actually. For now, I'm assuming that it is a Virasoro primary,
yes.
But you can ask the question that if it's not, if it's just a global conformal primary but not a Virasoro primary, does it still generate a black hole? I think that is still under research. Nobody knows the answer for the later question. But in this talk, I'm assuming it's to be a Virasoro primary. Here we see how the thermal physics kind of emerges from a pure state conformal block. And we'll see immediately that this means there's some problems. Already, if we take the semi-classical block and we take Lorentzian time to be large, we find that it follows this exponential decay. So the semi-classical vacuum block has information off. But we know that at any large but finite C, this cannot happen indefinitely. This means if I take the Lorentzian time to be larger than C, then this behavior should change. It should no longer follow this exponential decay. It should stop. This is what I just said. And you can estimate the time where it stopped using this condition, and this will give you this prediction for the time where it stopped decaying.
Is this where the heavy operator divided by C is the weight is becoming larger than, is becoming smaller than the weight of the light gun? You have H heavy over C, and you should compare that to HFL, right?
No, this is not the case. So
what's large mean for this?
This TH is related to, is basically proportional to 24 H heavy over C minus 1. So this is just a function of H heavy over C. So that behavior controls like how fast it decays. But the funny thing is when you match this condition, this TH cancels with the TH in the black hole entropy. So in the end, you get something that doesn't depend on H heavy. But the basic idea is that this formula only holds when your T is order 1. When your T is order C, your large C approximation breaks down, and this behavior should stop to be the case. All right, does that answer your question? Okay, great. And beyond that, we can see another signature of information loss, that is the forbidden singularities. If we look at the semi-classical block in the direction of the Euclidean time, you immediately see that there is a periodicity controlled by the Hopkins temperature. This is expected because if your system approximates a thermal system, then it better have periodicity along the Euclidean time direction. But from the safety point of view, this is absolutely absurd because it will map singularities when tau is 0. This is when tau is 0, the two light operators kind of collides, and there is an OP singularity there for the correlator. But this periodicity will map that singularity into all other places where this tau is like an integer. But for unitary safety, we know definitely that that cannot happen. A conformal block in a unitary safety can only have singularity at the OP points. In this case, it means tau equal to 0. So all these other singularities that are created by the thermal image should not be there. They're forbidden. So this is our second sharp signature of information loss that basically put the thermal physics of a black hole against the unitarity property of the CFT. Yeah, this is just more explanation for why the conformal block should not have other singularities, because in any other point away from the OP singularity, you can write the conformal block as a product of amplitudes of normalizable states. So they simply cannot diverge. So how to resolve these problems? We know that there is information loss in unitary CFT only in the large C limit. When you take C goes to infinity, a lot of what I said just breaks down. So you shouldn't be surprised that this happens. But when C is large but finite, no information loss is allowed. This means when C is large and finite, when you go to very late times, the exponential decay should stop. And when you go to the forbidden singularity, there should not be a divergent answer there. So how this happens? To answer this question is very, very hard because we do not know the closed form of Virasoro blocks in general. And we do not know the closed form of correlation functions in holographic two-dimensional CFTs in general. Question?
I was just wondering, how do you know that studying the vacuum block is enough to answer these questions?
Yeah, that's an incredibly good question. So one answer to that is for the forbidden singularities, we know that this problem must be resolved within the vacuum block. Because we can write the vacuum block as like products of normalizable states. So at the position of the forbidden singularity, the vacuum block should be finite. But for the late time decay, what you said is really a problem. In that case, there's no reason to believe that this late time decay problem is resolved within the vacuum block. In fact, with the most updated information we have, we actually think that's not the case. You actually need all these UV heavy states to be able to resolve that. I will come back to that later. So because we don't know the form of the blocks, we will have to rely on some very strange but useful special cases. In this case, my special case will be degenerate states. The degenerate operators or degenerate states are defined by the condition that there are some null descendants in its multiplet. For example, at level 2, you can impose this condition. So basically, it tells you that it have a null descendant null Virasoro descendant at level 2. These equations can only be satisfied when this weight h takes some very special values. For example, this is like 2, 1. So R is 2, S is 1. But in general, for any positive R and S integer, you have this expression at large C. For example, here you can see that for a 2-1 state, in the large C limit, you actually get a negative scaling dimension. That's scaling with C, so it's a very heavy but negative mass. But when R is 1 and S is some integer, then you actually have a finite dimension at leading order in large C. But that's also negative. So this is just the well-known result that when C is larger than 1, you do not have degenerate states with positive dimension. But we still can use this. For example, this equation, when you put this 2-1 state into a correlation function, this equation becomes a differential equation. So this V21 is just defined as the vacuum block in this 2-1 OLight state. This is how I define V21. But now of course, I think you will be asking this question, how can I use this method to study information loss when these states have negative mass and they have negative norm, they're not unitary to start with? This is indeed a good question, but I think the answer lies in analytic continuation. The reason that we can use this with some success is because the Virasoro blocks are actually simple analytic functions of the external dimensions. By external dimensions, I mean the dimension of these 4 guys. And it also only has simple poles in the central charge. So you can hope that certain properties of the Virasoro block in the unitary regime, where all the dimensions are larger than 0, is related to some properties of the same function, but with h taken to be negative. For example, the forbidden singularities are definitely still there when you change, when you take the h heavy to be from a large positive number to a large negative number. They're just placed in some different locations on the complex plane. So the right-hand side is the position of the forbidden singularities in the unitary case, and here is the position of the forbidden singularity in the degenerate case. For example, when we take this heavy state to be O21, it's a very simple heavy state, we only have one forbidden singularity that sits at 2. These other guys are not there for that particular case. So we can try to study what happens around that forbidden singularity. And then I will show you evidence that what we find is actually universal. So for this O21 state, we have that second order differential equation that we can solve in terms of a hypergeometric function. Here we take large C by taking B large. So basically C is just B squared. And with this hypergeometric function, we can study what happens near Z equal to 2, which is the position of the forbidden singularity. So this is the plot, and the red line is the semi-classical block. This position is 2, the location of the forbidden singularity. And you can see that for any finite C, you don't have the divergence here. But when you increase C, this bump becomes sharper and sharper. When C goes to infinity, it approaches the semi-classical block, and the singularity emerges. Of course, we can study this further by expanding the exact 2-1 vacuum block in the large C expansion. And this expansion takes this very simple form. Remember, B squared is just C. Now you can see something interesting. You may naively expect that, okay, in the semi-classical level, I have a forbidden singularity. Maybe when I include some quantum corrections, like some Witten diagrams, this will just go away. But this is explicitly not the case. You can see at each order in the large C expansion, there is a forbidden singularity at Z equal to 2. And that singularity actually becomes worse and worse when you increase the order of the large C expansion. This means that the forbidden singularity problem can only be resolved in the non-perturbative level. One way to probe the non-perturbative physics here is to do the Borel-Risson of this asymptotic series. As a reminder, a Borel-Risson is taking an asymptotic series which have radius of convergence equal to 0, and you improve that by adding a 1 over k factor into the series. And if that converges, you call that function, you get a Borel function. And you can try to recover your initial function az from the Borel function by this integral, if it converges. For our case of this 2-1 vacuum block, we get this function. This is our Borel integral. And we check that when this integral converges, it indeed produce that hypergeometric form that we recovered earlier. But of course, there are singularities on this Borel plane. So for some choice of z, this integral does not converge, and there is a singularity. These singularities are very useful and informative because they actually directly give you the non-perturbative effect, which I will explain now. So there is a simple argument that relates the singularities on the Borel plane to the saddles of the path integral. Of course, to do this, you're assuming that there is a path integral description for the 3D gravity. This first equation, this is our vacuum block. The first expression is just the definition of the Borel integral. The second expression is we have some sort of imaginative path integral expression for it. And this phi just in general represent the degree of freedom that we do path integral over. Now, to solve this equation, we can just request that B have this property. You just plug this in here, and you find that this equality holds. Now you use the property of the delta function, and you get that this is just this, the inverse of the derivative of the action. So now, in a singularity on the Borel plane, B goes to infinity, which means partial s partial phi is 0, which is exactly the condition of having a semi-classical saddle, or a solution to the classical equation model. Of course, another way to think about the non-perturbative physics is to write the large C expansion as a trans-series expansion, where the first piece is, this is the black hole classical background, and these are fluctuations or Witten diagrams around this particular solution. And then you have these non-perturbative pieces, which you can think of them as instantons. They're just exponentially small contributions in the trans series. And the additional saddles of the path integral correspond to these kind of contributions. Of course, please.
Is the singularity in your Borel plane the position of the true singularity? Sorry, I'm getting the Borel plane confused with the Z plane.
Oh, they're not really related to each other.
Right.
Yeah, so, yeah. So you can basically compute what this exponentially small piece is using the Borel plane just by doing a contour integral around the singularity. So this is exactly what we did, and the result is somewhat surprising. So in this particular 4-point function, we computed the exponentially small piece. And that exponentially small piece actually looks like another conformal block. It looks like instead of exchanging the vacuum and its dissidence here, this exponentially small piece looks like another conformal block that exchanges the 031 heavy state with all its Virasoro dissonance in this coordinate. But of course, I have to emphasize that we are not looking at this conformal block at all. This just shows up as a piece of the vacuum block. So what does this 031 type operators look like? So you know that in ADS, if you have a point mass sitting in the middle, if the point mass is very heavy, you get a BTZ black hole. But when it's not heavy enough, but it's positive, you get a deficit angle in a conical singularity. But when the mass is large but negative, like for this Degenerate operator 031, you get an additional angle. So instead of 2 pi, you add to this piece another piece of angle, and the conical singularity will look like this. So this is what we find as the non-perturbative piece in the vacuum block. Okay, so it seems like using this very simple example, we have found a lot of interesting things. We have found that the forbidden singularity cannot be resolved as a perturbative effect. It has to be resolved non-perturbatively. And the non-perturbative saddle associated with that is correspond to some weird additional angle geometry in the block. So you can ask how general it is. Is this just some sort of fluke that comes out of this specific simple example? Now I will show you evidence that this is actually what happens in the most general case. So first we can consider more general external heavy operators. Instead of O21, now I can consider R1. And R is from 2, 3, all the way to infinity, they're integers. For these guys, for each one of them, you have an rth order differential equation, that is the constraint equation from the null condition. And it's very hard to solve. But what you can do is you can zoom in to near the forbidden singularity. So for example, when this x is 0, when you don't have this term, this z is going to exactly sit on top of the forbidden singularity. And you can go a little bit away from it, parameterized by this x, and you take the large C limit and you keep x finite. Then you're zooming in really next to the forbidden singularity. If you do this, this rth order differential equation will simplify. It will become a second order differential equation. And this differential equation looks exactly like the 2-1 equation that we already studied. In particular, you can write its solution in this very simple form, and from here you can see like really transparently how does the forbidden singularity go away. For example, when you take C goes to infinity, this just gives you a power law singularity in terms of x times the gamma function in terms of h line. And that power law has a singularity at x equal to 0. But when C is finite, you can simply take x goes to 0, you just get a Gaussian integral here. And it's no longer divergent. And the reason that we believe this mechanism holds more generally is that you can expand this expression and you get this large C expansion. And you get this leading term that represent, if you believe that this mechanism holds for all Virasoro blocks, then this term gives an unambiguous prediction for what the large C what the first term of the large C expansion looks like for general Virasoro block. And you can check whether this is true by comparing to other methods that compute Virasoro blocks in this kind of limit, in a large C limit. To do this, you have to analytically continue R to the unitary case. So this R is related to the external dimension like this. So for the unitary black hole case, this piece, this square root is actually imaginary. So as long as you can, you analytically continue R into an imaginary value related to the Hopkins temperature like this term exactly matches the direct calculation from other methods in the unitary regime. So we believe that the mechanism we discovered actually holds more generally. Of course, beyond that, we actually also show that the kind of non-perturbative saddle here is also universal. This is not, I'm not involved in this work. This is done by Jerry Kaplan and Liam Fitzpatrick in this paper. And what they find is that the instantons in any large C expansion of any Virasoro block must be additional angles. And these additional angles correspond to the conformal block that exchanges a heavy operator O2p plus 1, 1. And if you go around the conical singularity in the middle, the angle you get is 4 pi p.
How are these related to higher spin fields in the block? These are all just higher spin operators, right? I mean, you're specifically saying there's spin 2p.
Spin 2p.
Just
That's not.
I'm not sure that's the case.
These are the weights in the.
Oh no, these are not the weights. These are the index of the degenerate operators.
Oh, I'm sorry, the A1 and the A2?
Yeah. R and S. I mean, they're not H and H bar. Yeah, sorry about that. Okay, so now what about the late time decay problem? This, as you mentioned earlier, this problem is much harder to solve than the forbidden singularity. You can, because it's UV sensitive, it's sensitive to other spectrums and the OP coefficients in your whole conformal correlator. But you can still try to make progress with what we have so far. You can take the differential equation that governs the near forbidden singularity limit, and you try to analytically continue that into Lorentzian time. You will get some result that looks like the exponentially decaying classical solution at first, but they will kind of go away from that at this time scale that we expect. But this result is not to be believed like very, very seriously, because by writing down this equation, you are ignoring some like 1/c terms, some subleading terms in large C expansion. When your Lorentzian time is this large, these terms actually become the same order as all these other terms are keeping. So it's not a controlled approximation. It's just something that you do to get intuition. Of course, at this point, you can see that you're just being stupid. There's a very well-defined way to compute these Virasoro blocks, and that is using the homological recursion relations. You can certainly do that. It's not a very efficient way, but you can try to optimize it slightly and make it run for a super long time. And we did that, and we were able to compute the coefficients of the expansion around z equal to 0 to 1200 order. And then we use that expression to study the late time behavior of the Virasoro block. So you can see this is a preliminary result. It's going to come out probably this month, probably the next, probably the one after. So here the parameter used is that C is equal to 30, H heavy over C is 1/12, and H light over C is 1/25. This black line represents the semi-classical block, so you see that it keeps decaying exponentially at late enough times. These are log scales, so a straight line here is an exponential decay. And this is the exact vacuum block that we computed. And you can see that initially it actually decays faster than the semi-classical block, but then it levels off. And the moment that it really goes away from the semi-classical block is roughly consistent with our earlier expectation of this time scale. But this plot itself is a little bit misleading, because you may say that, oh, you have already resolved the late time decay problem. But this is not true. If you look like really closely, this exact block is also decaying. So you can see a very slight slope downwards. And you can study that in a lot of detail, and you'll find that it's actually also decaying as a power law in terms of time. And we actually find that the power is -3/2. And that power actually do not seem to depend on the central charge, do not seem to depend on the external dimension. And currently we don't have a very good explanation for why this is so universal, but we're still trying to sort this out.
What about the little bumps?
Oh, those little bumps are just, I actually don't know like what physically they mean, but mathematically I know exactly how they come up. So this comes because we are defining our time as 1 minus z is like e to the minus it Lorentzian. So as you can see, when there's some periodicity here, right? Every time when t Lorentzian hits like 2/n, you're getting close again to one of the OP singularity. So numerically, you sort of see that by having these bumps, but there's no real singularities here. It's just maybe some phases lines up, but I'm not sure what's the kind of holographic interpretation of that. Okay, so we have partially resolved the late-time decay in the sense that we find the exact block indeed goes away from the semi-classical block at the time scale we expect, but it's not fully resolved because each Virasoro block still decays exponentially. This is actually quite expected because the vacuum block, if you look at the vacuum block in the, I'm sorry. So up to now, we've been working on this channel, heavy light, and we studied the vacuum block in this channel. But you can always use the bootstrap equation and you map this vacuum block to the other channel where you're just looking at the OP of a heavy operator, which is your black hole, and the light operator, which is your probe. They become some sort of a sum over different energy eigenstates here. So this is the other channel in the bootstrap equation. The reason that you actually do not expect the late-time problem to be solved here is that you can study what the vacuum block corresponds to in this other channel. And at least in the semi-classical limit, they correspond to a continuum set of states. So they're not discrete. So if you remember my third slide, the discreteness is the key for the decay to stop. But of course, this is like very hand-wavy. We don't claim to have precise understanding of it.
Why are you not concerned about the big mismatch right before?
Oh, you mean here?
Yeah, because
Um,
from your
yeah,
argument, I would have thought that it should track until it starts to go away, but now you have.
Well, I don't think I have such a strong argument. So what I can really, the only precise thing I can say is that in the beginning region, the exact block should match the semi-classical block. So when I increase t, it will depart at some time,
Yeah.
right? But it's
the-
not clear.
The
Like,
problem is it departs way before.
yeah, you're right, and it's actually going downwards. It's not like the decay stops here. So I mean, this is just a numerical result, and we believe it's correct. But even this estimate is just parametrical. There's no reason why this number cannot be multiplied by 2 or divided by 2. So it's not a precise prediction, I would say. The only thing we can say for definite is that within the time scale, within order of magnitude of this number, the two blocks should depart each other. Okay. So far I've been always using the CFT result, exact CFT observables and calculations to learn about quantum gravity. Of course, you may ask, what if ADS CFT is not so correct? What if it breaks down after the first large C limit? We actually try to check this by doing a direct bulk calculation. Of course, in 3D, you are armed with additional cheats. You can write the three-dimensional gravity as 2 copies of Chern-Simons theory, and the Chern-Simons gauge fields are related to the metric in this expression, where A is 1 copy and A bar is another copy. And then the holomorphic Virasoro conformal block is due to the Wilson line, the expectation of the Wilson line in 1 copy of the Chern-Simons. So you can try to compute what this Wilson line expectation value is in Chern-Simons theory, and then you compare that with the Virasoro block. We did this, and as far as we can check, these two results indeed match. In particular, this Wilson line approach in the block can produce the whole semi-classical block that I showed you that have all these information loss problems. But beyond that, the Wilson line was also able to reproduce the first quantum corrections around the semi-classical block.
Can you explain the picture? I didn't understand the picture.
Oh, sorry. This is one Wilson line. This is another Wilson line. So we're looking at a 4-point function, right? So basically, there's one Wilson line connecting the 2 light operators, and there is another Wilson line connecting the heavy operator. Okay, so this is basically everything I have today. To In summary, we have explained that information loss indeed show up in the semi-classical limit of a unitary CFT. In particular, there's two sharp signatures for information loss. One is late-time decay, and the other one is forbidden singularity. We were able to resolve forbidden singularity in many examples, and we have reason to believe that this resolution holds more generally. And we partially resolved the late-time decay problem. Of course, in the end, we also checked ADS CFT duality at the first quantum level. As for future directions, all of this, the very philosophical goal of all this work is to understand the path integral of quantum gravity. But more specifically, we want to understand what's the meaning of the non-perturbative saddles being these unphysical surplus angle geometries. This is not really surprising because a lot of instantons are in configurations that are not like physical in some sense. For example, you can have like complex instantons in gauge theory. But in this particular case, we want to know what this additional angle means in the context of ADS-3 gravity. And we want to be able to really resolve the late-time decay problem, maybe requiring that it do not have late-time decay, it just keeps oscillating. We'll put some constraint on what the spectrum is for a 2D CFT. That is still under investigation. And in the end, we want to be able to say something about the firewall paradox, and that will involve doing local bulk reconstruction. And we are trying to expand our Wilson line formalism to be able to do that. Okay, thank you.